Hello to everyone. My name is Dimitrios Kolias, and I'm Associate Professor in Multimodal AI at Queen Mary University of London. And the title of this talk is Recent Advances in Proactive Comorbidity Prediction in HIV Towards Fair and Trustworthy Care. So, advances in ART, antiretroviral therapy, have transformed HIV into a more chronic and manageable condition. People that live with HIV compared to the past, they live much longer, but unfortunately the burden of comorbidity has increased. And some comorbidities are the cardiovascular or metabolic or that have to do with the mental health or with cancer and any other diseases. Current screening is reactive, symptom-driven, and often late. So routine EHR, electronic health records, lab tests, and demographics are underused currently for proactive screening. So this brings a chance here for AI that we can build tools that can provide early, fair, when I say fair, I mean unbiased predictions, unbiased models, trustworthy, comorbidity predictions, and early risk stratification tools that can enable more proactive HIV care. As is the case with all the medical domain, in order to create AI tools, we need datasets. So one contribution that we have done is that we have collected one large dataset from a clinic in South. We are at Queen Mary and we are in London, in the UK. So we collected real-world electronic health record data from almost 2,200 HIV positive patients from Southeast London clinics and also some other specialist HIV services within spanning a 12-year period from 2012 until 2023. And those data consisted of 30 lab microbiology and biochemistry variables, 7 social and demographic variables. I'm going to show you them in the next slides. And finally, 12 top-level ICD-10 diagnostic categories. Some examples here I'm showing, let's say the A00 until B99, they have to do with infectious diseases, or the code I from 00 to 99, they have to do with circulatory diseases, and so on. And here you can see what are all the different features that we used, and also what is the corresponding description, and what is the expected normal range. Now, generally, I need to mention that the normal range is something that it is in a lot of cases dependent on the gender and the age of the people. Keep this information because a bit later in the presentation, I'll come back to this. These here are other features that have to do with the demographics and the social features. For instance, you can see we have the age that we have grouped them into 4 different groups, from 20 to 40, from 41 to 60, 61 to 80, and until 100. Generally, we have a lot of different distributions in those features, and that is generally expected. We also had the gender, we had the race, because the clinic was in London, we had a lot of different ethnicities and people were coming from a lot of different continents of birth. But again, I need to mention that there is always some imbalance here. For instance, you can see that we didn't have that many Asian patients. And I need to mention that this is an ongoing work because we are currently extending the database in order to have more coverage in terms of more people from each race. And other features had to do, as I said, with the continent of birth or the sexual orientation, if the people were or were not currently or previously commercial sex workers, and what was the root of the HIV infection. And those are the diagnostic categories. For instance, they have to do with any form of comorbidity and disease that you can think. They can be factors influencing the health status and the contact with the health services, or diseases of the digestive system or of the respiratory system, and so on. And again, what I was saying before still stands here, that we have a lot of different imbalanced classes. And let me also mention that those factors, those categories that you see here, they are not mutually exclusive. So every patient can have at least one and even more multiple of those that you see. And what we did in a work with my fellow student Solomon Russo and my colleague Kiani Zhang, both all from Imperial College London and from the King's College NHS Trust here in London, in the UK, is that we developed a deep neural network that can take as input all those variables that I presented to you previously and give us output the 12 diagnostic categories. So this is the whole architecture. Let me just now go into each specific part. I will not delve into many details about, mathematics formulas, but I'll just say the higher level what each block is doing and how this is doing it. So starting initial, the input, the lab test, and let me also mention here that generally we had two different settings, two different scenario. The one was, as we call it, the demographic aware approach, in which as input to the model we put both the 30 lab tests and also the demographic and the 7 demographics and social features that I presented you previously. And we call this demographic aware because the model gets an idea of both the lab tests and also the demographics of the patients. And the other is the demographic unaware approach, in which the model has as input only the 30 lab tests. So that's why here I just write input because it could be any of the two. That was a parenthesis. So coming back. So the input features are first inputted into the initial block, which maps the raw features into a learned feature space. This is typically done. It consists of multiple dense layers. Then the cross-feature interaction block follows, which explicitly models the interactions between the features that was not being done in the previous stage. For instance, this module captures patterns like that some particular patients have high BMI, body mass index, and low CD4. Then the next is the attention-based residual block with learnable fusion. The aim is that it will create a robust denoised representation of the interactions of the lab and the demographic input data. And it has built-in skip connections for better optimization. So we can decompose this into 3 parts. The one is that it has a residual block and acts like a residual block. The second is that it consists of attention mechanism, that the whole idea is that the attention we want to learn which dimensions of the residual features are important, and it will downweight the noisy ones. And the last one is the learnable fusion that lets the network decide per each feature how much to trust the refined path versus the original interaction of the features. The next component of our method, which by the way, I think I forgot to mention, it's called Comorbidity, is the dual attention block that consists of both a channel and an interaction-based spatial attention. So the aim of this block is that we want to help the model to focus on only clinically meaningful lab and demographic patterns and to dampen those that are either redundant or noisy. So this consists of some channel, as I mentioned before, some channel attention that learns which of the latent dimensions are globally important and boosts or suppresses them accordingly. Then we have also the spatial interaction attention that the aim is to help the model to modulate the representation based on the learned feature interactions. And the last one is the combined attention, which enforces that the features must be important both as standalone channels, but also in the context of the interactions that are strongly expressed. Then we have the bottleneck block, which serves as a shared latent space from which all the comorbidity tasks can be predicted in the next stage. It forces the model to compress the information into a compact, high-level representation of the state of the patients. And it acts also as a regularizer, so it can encourage the network to capture the informative features compared to those that are non-informative, redundant, or even noisy. And the final component of the Comorbidity net is that it consisted of a label-specific attention head which learns a small disease-specific gate that reweights the bottleneck differently for each comorbidity. We had 12 comorbidities, so we have 12 different heads. And this allows each disease to focus on its own relevant subsets of the labs and the demographics and generally the input data, reducing any negative transfer that can arise. Because, as I mentioned initially, those 12 outputs, this is a multi-label classification problem. So this means that one patient can have multiple of the 12 comorbidities. So there could be a case that there could be some negative transfer between those tasks, and that is why one of the reasons why we have this component. And as I mentioned before, we have two different settings, the demographic aware and the demographic unaware ones. So here, let me present you some results. Generally, we have a lot of different results and a lot of analysis that I will present to you. So here, first of all, we compare the performance of the Comorbidity, the proposed network by us, in terms of the demographic aware approach. So that means that the model was taking as input both the 30 lab tests and also the demographics and the social features. And the demographic unaware approach, which was when the model was taking as input only the 30 lab tests, and that's it. And we did this for a lot of different methods. So we compared the performance, of our model. So we used TabNet, which is one very typical deep learning model, having generally state-of-the-art performance for when we're dealing with tabular data, like the features that we're dealing with. And the surprising here was that this was among all the other methods that we compared the state of the art, this was as a deep learning method, it was the one that produced the worst performance both in the demographic aware approach and the demographic unaware approach. Then we also used logistic regression, random forest, MLPs, artificial neural networks. We tried a lot of different variations, and then with the boosting the LGBM and XGBoost. As you can see here in this table, there are some things that I want to note, and they are important. So the first one is that our method surpassed all other state-of-the-art baselines, both in the demographic aware and in the demographic unaware approach. That's the first one. Secondly, this is what I will say stands both for our model but also for all the other models, that generally the demographic aware approach produced higher performance than the demographic unaware approach. And the last one is that, as I said, the tabular net had the worst performance. Then the random forest and the MLP had like the mid-level performance. And as expected, generally the boosting methods had the best performance. Below, however, the performance of our model. And here, and also let me just mention that here I'm just showing you the performance in terms of the macro F1 score. Macro F1 score, it means that we compute what is the F1 score per each comorbidity, and then we average those. And similarly, here I'm just showing you in a little more detail about for each method, for our model and the other models, both in the two settings, demographic aware and demographic unaware, for each comorbidity, what was the F1 score that they achieved. Again, I need to mention here that our method outperformed all other methods in almost all comorbidities, apart from the last one, the Z one, that it's very small, like 0.1% less performance. Also, I need to mention here that, again, for all the models, the demographic aware approach produced better performance for each comorbidity, and that it was for all methods, including our own. And generally, we can see that for some classes, for some comorbidities, all of the methods had very good performance. For instance, as I said, the Z category here, they all had like more than 90%, which is a very good performance in terms of F1 score. But on some others, for instance, the M categories, the performance of the model was significantly lower. Generally, this is expected, and one of the reasons this happened is because of the distribution of the data that we had. If you remember when I was presenting you the 12 categories, the 12 classes, I was telling you that they are imbalanced. So this plays a role. But in all cases, our model had achieved the best performance for all of them, and all of the performances are. We have some low, for instance, the G1, but they are not very, very low. I mean, for instance, some other methods, they had like almost 0% performance on some cases. We didn't have any such case for us. And then the next part of the experiments is that, in whenever, especially when we're dealing with in the medical domain, it's important, of course, to create a method that has a very good performance according to some specific performance metrics and indicators that you have. But that's not only it. We're also interested about understanding a little more, and that is important for interpretability, for explainability, and for clinical trust. And I'll come back to that. So what we did afterwards, this was that we got our model, and then we tried to understand, we did some feature important analysis. So this means that we were trying to understand for each comorbidity, which were the features that played the most important part in the decision of the model. And one example that you see here is the comorbidity, the N00 to N99. This has to do with diseases of the genitourinary system. And in such cases, and also some others that I don't present here, and you can have a look in the paper if you want, we have found that some comorbidities are biochemically driven. In this one, you can see that, let's say, the most important ones are creatinine and estimated GFR, which is also clinically relevant. I'll come back to this in the after 2 slides. I'll explain a little more about that. So the first observation from the feature importance is that for some comorbidities, they're biochemically driven. Another observation is that for some others, they are demographically and socially driven. So this means that the most important features are the demographics ones that have to do with the gender, the age, the continent of birth, and the gender. And here I'm just showing you one example that this is the category F01 to F99 that have to do with mental and behavioral disorders. And as you can see, this is mostly dominated by the continent of birth and secondly, the sexual orientation. But the continent of birth, you see, it has a big difference. That's the top one feature with a big difference from the second. So, in terms of clinical interpretability now that I was mentioning before, we showed that the predictive drivers of comorbidities are largely clinically interpretable and also label specific. For instance, as I told you before, for the category N, the creatinine and the eGFR dominate, and that makes clinical sense. And that's not because I tell you, but when we were doing these experiments, in order also to construct the data set, we were having a lot of collaboration with medical experts, and especially my student, he's also working in the NHS Trust National Health Service systems. So those are validated by experts. So yes, generally, as I said, it makes sense because generally the creatinine and the eGFR are for kidney disease. They are the hallmarks. Or another example is the class D50 to D89 that have to do with blood and immune diseases. In that case, we found that hemoglobin overwhelmingly dominates. And again, hemoglobin is a signature for anemia. So again, this clinically makes total sense. Or I have 2 other cases here. The one that I described previously, the F1, we found that firstly the continent of birth and then the sexual orientation dominate. And that also makes sense because the continent of birth, there are a lot of people that had to migrate and so on. Therefore, this created a lot of stress and also the stigma and all those cases were, let's say, not easy and people who had a lot of stress. So it makes sense that this is more dominated by the place where people are rather than some other, let's say, lab tests. And the last example that I have here is the code J00 to J99, the respiratory. And we found, let's say, that albumin was the most important feature here, which again makes sense because albumin is a sign of vulnerability in terms of the immune and the nutritional system of the patients. Then we performed another experiment, which I think all of them are structured. And I think that's generally how people should be thinking. The first one is that you want to create a system, an AI model that has very good performance on a particular task that you want. The second is that you want to check whether to verify and validate whether indeed the model has a good performance because it has learned the actual problem and it's not that it has found, let's say, a shortcut or some noise or in a way it is cheating, if you know what I mean. Yes, and the last one is that because we had two different settings that I tell you, that we had the demographic aware and demographic unaware, we are also interested to see about the models to be fair, to be unbiased. But it's not only the models, the bias can also exist in the data set. So what we did is the demographic recoverability experiment, where we took as a model the XGBoost, and we put as input either just the lab test or the lab test and the 12 comorbidities. And as output, we had the demographics. We had the gender, the age, the race, and the country of birth. So with those experiments, we wanted to assess how well the demographic features can be inferred from the clinical variables or the clinical variables and the comorbidities. So this is called proxy leakage. And we had some interesting findings that, again, they are explained as I will present in a bit. So the first one is that the gender can be recovered, both from the lab test and the comorbidities. This is F1 score again, almost 93%. Age and race also they also have a high F1 score and they can also be recovered. And the country of birth is the last one that had the lowest one, still recoverable, but not that much. So this gives us a lot of interesting findings. So the first one is that if you compare the two rows, when we input also to the model the comorbidities, they don't contain much demographic information, because if you see the performance in the gender, there was no increase in the performance. In the age, it was like a small increase. Race also very small increase. In the country of birth, also very small increase. So that is the first one. The second is, I think I have it after one, yes, that this aligns with the observation that we had in the previous experiments, that we found that the demographic aware methods outperform the demographic unaware. And if you really think about this, it makes sense. When the model was taking as input only the lab tests, because we see here that from the lab test, we can infer, we can find the model. So indirectly, the model could understand the gender, the age, the race, and the country of birth. Not perfectly, but it could. So there was like some noise there. Therefore, it makes sense that if the model didn't have this as input, the demographics, it could try to infer it from the lab test, and that created some issues. Therefore, the performance was it was lower than when the model had the demographics as input. Therefore, it didn't have to retract them from the lab test, and it could just only, let's say, focus on doing correctly the comorbidity classification. So from a medical perspective, the demographic attributes are not merely ancillary, but are deeply intertwined with lab test interpretation. And the important is that, and now, if you remember when I was when I was presenting to you the input features, the 30 lab tests, and I was showing you the description, and there was also another column with the normal ranges, I told you that the normal ranges are also dependent on the gender and the age. So many reference rates for lab values are stratified by the gender and age. So by default, this explains a bit the result that we got with the demographic recoverability. And also it's important to mention that some prior studies have also demonstrated consistent demographic patterns in disease risk and biomarker distribution. Of course, there are also some implications now with this. So even when the demographic features are excluded, the model may still implicitly use them via correlated lab markers, as I was explaining to you previously. And this raises concerns about fairness, bias, and interpretability. So using demographic data can enhance the predictive power, we have seen that, but this must be done responsibly with awareness of bias risks. And what I would say is that I think that it's important that the models, at least, let's not generalize for all the medical tasks and so on, but at least for the specific one that we're dealing here, that the model should use the demographics, but this needs to be transparently and with safeguards. It's important. And generally, a fully demographic agnostic model is rarely achievable in medicine, generally speaking, because of biological differences that are embedded in lab tests. What we found here, it's not something, we didn't discover Antarctica. It's something that also other researchers in other fields, they have found out. Not necessarily the same thing, but generally that there exists noise and bias in the data, either clinically relevant or non-relevant. So that was it. Thank you very much. And if you have any questions.